Okay, now let's take a look at economic growth of the 10 largest economies in the world. And we're going to look at 2016 data here. So the first column shows the actual growth in overall real GDP. And it looks like India tops the list at 6.8%, followed by China at 6.7%, and then Indonesia at 5%. These relatively high growth rates are not surprising because we expect countries that start out poorer to have higher growth rates than those that start out richer. And then you notice that we have a couple negatives in here. Brazil at negative 3.6, so serious contraction there. And then Russia with about 0.6% contraction in 2016. The other countries like France, the UK, Germany, Japan, and the US all hover around 1 to 2%, which is what we generally expect for most industrialized countries. This is telling, right? The growth rate of GDP gives us a sense of how fast that pie is growing. But we also know that the population is growing as well. And if we consider population growth, we can then get to the growth in real GDP per capita, which is a better indicator of standard of living, as we discussed previously. So, for example, if you take China's growth rate of 6.7% and you subtract from that the growth rate of the population of 0.41%, you get a real GDP per capita growth rate of 6.29%. So even though the pie grew by 6.7%, the slices only grew by 6.29. Not bad, because China purposely restrains their population growth through various strategies, and that helps keep the per capita growth more aligned with overall growth. The situation is somewhat similar for India, right, as well as Indonesia. And so all three are high growth rate countries and high growth rate of GDP per capita countries because they keep their population growth relatively low. Contrast those countries with Brazil, where we shrunk, or they shrunk the pie by 3.6% and grew the population. So if you take negative 3.6 and subtract 0.73, you get negative 4.33. So they actually contracted their GDP per capita, their standard of living, more than the overall contraction of GDP by growing the population. Anyway, this is a good way to think about growth of the pie versus the growth of the slices, and realize that just because countries are growing the overall GDP doesn't mean they're enhancing the standard of living of the people there. Next, let's take a look at how we might calculate the growth rates over a period of time. For example, if you know what the gross domestic product in the US is today, and you know what it was in 1900, you could calculate the average annual growth rate each year in between. So effectively 120 years of growth rates. And the formula we use is this one. It's called the compound annual growth rate. So what I'm going to do is pull up some real data here. This data is from the Federal Reserve Economic Database, and it gives us a chart that actually identifies GDP in every year going all the way back to 1947. It's quarter by quarter. So let's just pick two periods and calculate the average annual growth rate in between. Okay. Let's go ahead and start with quarter one of 1950. And it looks like we've got about $281 billion. Okay. And then let's go forward to the most recent data that they have in here, which is quarter two of 2020. And that's going to be 19,000 billion 486. Okay. So we're going to be comparing these two periods. Okay. To do that, we use this formula right here. And let me pull this up on the overhead so you can see the formula here. Okay? And then we've got our data that we just pulled. Okay? So we're just going to plug in the numbers. Okay? Our current GDP, that is the most recent, would be 19,486 billion. Okay? We're going to divide that by the previous GDP, which is 281. Okay? And then we're going to take that to the power of 1 over, I put n here. In the previous slide, it says number of years. Okay? It doesn't matter. N is the number of years. And how many years do we have? Well, we go from 1950 to 2020. That's 70 years. So we're going to put 70. Okay? And then we're going to subtract 1. Now, if you do that, you will get about 6.2%. 0.062. Okay. So that is the growth rate of GDP from 1950 to 2020 per year in the United States. Now you look at that and you say, oh my God, that's like India, right? That's like China. That's a lot. But keep in mind, we used nominal GDP. We didn't use real GDP. Okay. If you go back to the data, look at what it says here. Okay. It actually says gross domestic product, okay, in billions of dollars. So this is not adjusted for inflation. If we want to do the inflation adjusted GDP, we can do so by choosing real GDP. And notice now it says real gross domestic product, and it's in billions of chain 2012 dollars. That means we're adjusting everything to 2012 prices. And if we use that data, quarter one 1950 becomes $2,185 billion, and 2020 quarter two becomes 17,282. So using that data, we now use the same formula but with the real GDP. I'll put up here nominal GDP to separate that, and then real GDP. We plug in our numbers, right? Our numerator is 17,282. Our denominator is going to be 2185. We're then going to take that same thing, 1 over 70, and then we're going to subtract 1. And if you do that, you will get about 3%. So that's the growth rate in real GDP, which, if you compare the two, implies that we've had about 3.2% inflation on average over that time frame. Anytime we're calculating growth rates, we use real GDP, not nominal. Okay, now let's go back to our growth data and talk about the rule of 70. The rule of 70 helps us understand how long it takes an economy to double in size based on its actual growth rate. Okay? It's a very simple formula. Take the number 70 and divide it by the growth rate. Okay, so if, for example, an economy grows at 1% annually, you take 70 and divide it by 1, it would take 70 years for that economy to double. If instead the economy grows at 2% per year, then it would be 70 divided by 2. It would only take 35 years to double. And you can continue on. I mean, there were periods where India and China were growing in double digits. So imagine a 10% growth rate. Well, that means 70 divided by 10 is 7 years to double. During those time frames, some countries were growing at 1%. So you have what we call convergence, where the countries that grow at 10% are doubling every 7 years, whereas the countries that are growing at 1% are doubling every 70 years. So convergence means those high growth countries are converging with the lower growth countries. And this plays into the poor versus rich countries as well, because if we accept the premise that poor countries are going to grow faster than rich countries, then over time, poor countries should be doubling their economy more frequently than rich countries, meaning poor countries will converge with rich countries. I want to be clear, though, that it is not always acceptable to assume that poor countries grow faster than rich countries. Okay, there are plenty of countries that are poor that have stayed poor and not only have not grown, but have actually regressed over time. Okay, we'll talk more about that later on. But in essence, for convergence to exist, countries must share similar social, political, and economic institutions. If they do, then we would generally assume that poor countries will grow faster than rich countries. Okay, let's move on to efficiency. Efficiency is the effectiveness at utilizing limited resources to maximize the standard of living and economic growth of a nation. Okay. We often talk about efficiency in economics because of the problem of scarcity. We have limited resources and all these unlimited wants, and if we don't operate efficiently, then we're not satisfying all the potential wants. There are two types of efficiency. There's allocative and technical. More specifically, allocative efficiency is where we allocate resources towards the right goods and services. This means the producers make the things that the consumers want. If you are the producer and consumer, like in our day-to-day lives, then this naturally occurs. If you say, I want cornflakes for breakfast, then you're going to produce cornflakes for breakfast. If you say, I want decaf coffee, you're going to produce decaf coffee. But when you separate the producer and the consumer, you can get allocative inefficiency, meaning that maybe Starbucks makes a lot of decaf coffee and people don't really want that. Well, that's inefficient. Or General Mills makes cornflakes for people to buy and nobody buys it. Okay? So that's allocatively inefficient. Allocative inefficiency is something that can be rectified once we recognize that we produce things people don't want, but there is a period where there's wasted resources. Technical efficiency, in contrast, implies that we're producing our goods in the most effective way. And there's actually two subcategories of technical efficiency. There's static and there's dynamic. Static is where the economy is producing at capacity at a point in time. And we can illustrate this concept with a production possibilities frontier. Recall that a production possibilities frontier breaks the economy down into two categories of goods. Here we have capital goods on the vertical axis and consumer goods on the horizontal. We then illustrate the production possibilities frontier, which shows the different combinations of these goods that can be produced given our limited resources. You can ignore this one too for now. So our limit is production possibilities 1. Okay? We can choose any point on the curve or inside the curve. If we are statically efficient, it's implied that we are producing on the curve. Static inefficiency would be inside the curve. And that's a problem because think about point D. At point D, I can actually get more consumer goods without giving up any capital goods. I can go from here to here. I can get more capital goods without giving up any consumer goods. I can go from here to here. So I'm operating with idle resources that would be more effectively utilized, getting me to the production possibility frontier. Technical efficiency can be measured with a capacity utilization ratio. Here's some data from the Federal Reserve. The more recent data, say May 2020, is 64. That means we were at 64% of capacity. If you go back to 1973, November, it was at 88 capacity. The average over time is about 80. That's one way to quantify how close we are to our production possibilities frontier in the US. We're never going to be on the curve. That would be 100% capacity utilization ratio, but we can certainly try to move closer to it. Finally, having static technical efficiency implies lowest cost production because you're getting the maximum output for a given outlay of resources.